Hello and welcome. Today we're taking a deep dive into a true cornerstone of electrical engineering, the power transformer. It's a game-changing invention from the late 19th century that, quite literally, made our entire modern AC electrical grid possible.
And to get us started, let's just get a sense of the scale we're dealing with here. These are not small devices by any stretch. We're talking about massive, static machines that operate at hundreds of thousands of volts and handle power ratings that can soar into the hundreds of megavolt amperes. They are the absolute bedrock of our electrical world.
So here's our roadmap for today. We're going to move from the first principles all the way up to the intricate engineering of a real-world machine. We'll kick things off at the fundamental physics, then build up an ideal model, and finally we'll deconstruct the high-power systems that form the very backbone of our grid.
Okay, let's dive right in by revisiting the core piece of physics that makes any of this possible in the first place: electromagnetic induction.
It really all boils down to this one concept: mutual induction. You see, a voltage is only induced in a coil when the magnetic flux linking it actually changes. That change, the rate of change of flux, is the absolute non-negotiable requirement for the whole thing to work. No change, no induction. Simple as that.
And this illustrates a really critical point. Transformers are fundamentally AC devices. If you try to hook one up to a direct current supply, you'll get a static magnetic field. And with no change in flux, there can be no induced voltage. It just won't work. It's the constantly alternating nature of AC that is absolutely essential for the entire process.
Okay, so now let's see how we can take that principle and build it into the idealized model of a transformer. We'll focus on its essential components and, of course, the inherent challenge of energy loss.
At the heart of it all is the ferromagnetic core. This is the critical pathway. It provides a path of really low magnetic reluctance. You can think of it as the magnetic equivalent of low resistance in an electrical circuit. It's basically a superhighway for guiding the magnetic flux from the primary to the secondary winding, making sure you get maximum linkage and you minimize any wasteful leakage. But there's a catch. Because the core itself is made of a conductive material, that same alternating flux that's so useful for inducing voltage in the secondary winding also induces these unwanted little loops of current inside the core itself. We call them eddy currents, and they do absolutely nothing useful. They just generate heat. And this is just a brilliant bit of engineering. Instead of using a solid block of iron for the core, it's actually built from thousands of very thin sheets or laminations. Each one is coated with an insulating varnish. This structure creates a really high-resistance path that effectively blocks those eddy currents from flowing, which drastically reduces heat loss and massively improves the transformer's efficiency. So, here's the crucial point. The way a transformer changes voltage is, well, elegantly simple. It's all dictated by the ratio of the number of turns of wire between the primary and secondary windings. If you have more turns on the secondary, you step the voltage up. Fewer turns and you step it right down. Right, with those fundamentals established, let's scale this whole concept up to the three-phase systems that are the real workhorses of high-powered transmission and distribution. They're just far more efficient for moving huge amounts of energy around. Now, while the induction principle is identical, the actual physical construction can vary. In what we call a core-type transformer, the windings wrap around the core's limbs. But in a shell-type, the core effectively wraps around the windings. Which one you choose is a pretty complex engineering decision that comes down to things like cost, how you're going to manage heat, and how you'll manage insulation stress.
Okay, now let's pop the lid off the tank and really deconstruct the sophisticated components that make up a modern, high-power, three-phase transformer.
This table gives us a fantastic summary of the differences. You'll see the low-voltage winding is placed closer to the core. That's mainly because it's easier to insulate, and it has to handle enormous currents, sometimes thousands of amps. The high-voltage winding, on the other hand, sits outside. It carries lower current, but it needs much more robust insulation and a totally different winding style to manage all that electrical stress. So, how do you handle that immense current in the LV winding without big eddy current losses inside the conductor itself? Well, engineers came up with this really clever solution. It's called a continuously transposed conductor, or CTC. It's basically a cable made of lots of smaller, insulated strands that are methodically woven together. This ensures that every single strand occupies every possible position within the conductor's cross-section, which makes the current distribute itself perfectly evenly.
And for the high-voltage side, you've got a different challenge: managing electrical stress. For that, we have the continuous disk winding. Here, The conductor is wound into a series of flat spirals, or discs. This creates a much more uniform voltage distribution right across the winding, which is absolutely essential for preventing the insulation from breaking down under those high voltage conditions.
Getting that high voltage safely out of the grounded steel tank requires another incredibly sophisticated bit of engineering: the condenser bushing. By layering conducting foil and insulated paper, it effectively creates a series of capacitors. This whole structure acts like a voltage divider, making sure the potential drops gradually and uniformly from the central conductor down to the grounded flange, which prevents a catastrophic electrical arc.
Finally, a transformer doesn't just operate in a vacuum. So let's look at the critical ancillary systems that allow it to function reliably under the constantly variable load conditions you find on a real-world power grid.
The on-load tap changer, or OLTC, is actually one of the few moving parts in a transformer. It's an incredibly complex switch that allows the utility to slightly adjust the transformer's turns ratio by selecting different taps on the high-voltage winding. And the crucial thing is, it does all of this while the transformer is energized and under full load. This is absolutely vital for maintaining a stable output voltage as consumer demand goes up and down throughout the day.
Think of these as the transformer's life support systems. You've got the main tank, which contains all the active parts, and it's filled with a special mineral oil. This oil serves a dual purpose. It's an excellent electrical insulator, and it's also the primary medium for cooling everything down. Then, that smaller conservator tank you see on top acts as an expansion reservoir, making sure the main tank stays completely full as the oil expands and contracts with temperature changes.
You know, it's a remarkable testament to the elegant efficiency of mutual induction that this foundational 19th century design remains so absolutely central to our 21st century lives. Its simplicity and its sheer reliability are almost unmatched in heavy electrical engineering. And that really leaves us with a compelling question to think about. In an age of such rapid technological disruption, what could possibly challenge a design that's already so close to perfection? What will power the next century?